Okay, welcome back to Quantum Field Theory, a student's perspective. Today we're doing the Feynman path integral for the harmonic oscillator. And we finished with this formula. It looks pretty messy, but actually we're just going to do a standard completing the square. We're going to change variables and complete the square. So these were our Fourier transform variables, the tildes and the non-tildes. And this was eventually, this whole formula here is eventually our objective. First of all, I just want to point out it might happen if we have something like e squared minus omega squared plus I, e squared plus omega squared, epsilon. Epsilon is infinitesimal, so this is a positive number, so this whole thing is just the same thing as I delta, and then we rename delta I epsilon. So don't worry, if you think I'm not keeping track of these things, we just don't need them because this is infinitesimal. So what we're going to do now is we're going to change our integration variable. We're going to complete the square. I'm going to introduce x tilde e is equal to q tilde e. Actually, I'm not sure if this might be chi in the book. I'm just going to call it x plus f tilde e divided by e squared plus omega squared plus I epsilon. So this is a constant term. It doesn't depend on q. And in a sense, all we're doing is making a translation of the transformed variables. And the important thing is that even though we didn't define what dq is, we're going to make sure it's equal to dx. So doing this constant thing, this will happen. Okay, so we have this formula here. When I go through this whole thing, and I'm not gonna, it's done in the book and it's just a matter of grinding through it. I don't want to grind through the whole thing, but this s will become, s is equal to 1/2 the integral from minus infinity to infinity dE over 2 pi x tilde e e squared minus omega squared plus I epsilon x tilde minus e minus f tilde e f tilde minus e divided by e squared minus omega squared plus I epsilon. So this is the result of changing the variables, and now we take this s and we put it in here. So remember, this whole thing was s there, and so I'm going to erase this now. I'll erase it after I put it on the board, but we get what our final formula is equal to e to the minus I over 2, the integral from minus infinity to infinity. The minus sign comes from, we're going to take this last term. This term has no dependence on q, so we don't have to worry about it with the path integral. So I get e to the minus I over 2, the integral from minus infinity to infinity dE over 2 pi f tilde e f tilde minus e divided by e squared minus omega squared plus I epsilon. And we don't need this anymore. Now I can erase this. We're just going to put the dq part here. Only it's dx now because we changed variables. So it's that times the integral of dx e to the I over 2, the integral from minus infinity to infinity, d over 2 pi x tilde e squared minus omega squared plus I epsilon x tilde minus e. So this is our big formula. And I know a lot of you are thinking this is all very abstract and everything. What do we use it for? But you can already see the structure of Feynman diagrams coming in there here. For those of you who have done them, you'll notice this e squared minus omega squared minus I epsilon in the denominator, plus I epsilon. I'm used to the other metric. I always say minus I epsilon. It's plus I epsilon in this metric. This is already the structure. You can see the propagator of a scalar field. And so we'll get there. I think the next lesson or two afterwards we'll start showing how all of this leads to the Feynman diagrams. For now, let's just see one thing. If we set f equal to 0, f is 0, 0, 0, this is all 0, e to the 0 is 1. So we're just left with this thing. We know when f is 0, the vacuum ground-to-ground transition amplitude should be 1. When there's no driving force, nothing happens. So if we're in the ground state, we stay in the ground state. So that means this whole thing here, this path integral, which we don't know how to evaluate, is equal to 1. In a sense, we're setting the normalization. So we end up getting that our ground state to ground state transition amplitude in the presence of a driving force is just this part over here. So I'm not even going to write it again. I'm just going to say when f equals 0, we just erase this part because it's equal to 1. And this is our ground state to ground state transition amplitude. And we can now do some manipulations here. We can go to the time domain. I can write this as, I can put back the Fourier transform variables, put back the time domain, and we'll get something like 0, 0, f is equal to e to the minus I over 2, integral from minus infinity to infinity. We're going to get two integrals because we got two of these things. dt, dt prime, f of t, and I'll have an energy integral, dE over 2 pi, e to the minus I e t minus t prime divided by minus e squared minus omega squared plus I epsilon. This minus sign and this minus sign just cancel. I just wrote it down there. Then f of t prime. So this is, if we go back to our original time variables, this is the ground state to ground state transition amplitude, and we'll often write it as e to the I over 2, the integral from minus infinity to infinity, dt, dt prime, f of t, g of t minus t prime, f of t prime. And all we did is I'm just naming this thing over here g of t minus t prime. So I'm going to come back in the next video and we're going to evaluate. This is the Green's function for the system, and I'll write down the equation that the Green's function satisfies. It's pretty obvious. That's just a harmonic oscillator equation, and I'll just evaluate it using residue calculus, fairly routine calculations. But just in case you haven't seen it in a while, we'll get to it. So I'll see you on the next video.